Our sun, it fuses hydrogen into helium within its core, and this process is very energetic. It produces lots of heat and light, which we make good use of. But that's not the only purpose for all that energy. The energy of that fusion also keeps the sun from collapsing. The pressure created by all that energy in the core of the sun pushes back against the force of gravity that's trying to pull the sun in on itself. And so the sun sits in a state of dynamic equilibrium, furiously burning fuel just to stay the same size. But the fuel in the sun is limited. The sun has maybe enough hydrogen to last for 12 billion years, and we've already used up 5 billion of them. So in about 5 or 6 billion years, when the sun has depleted the hydrogen in its core, the core will collapse and begin to fuse that helium into carbon. And it can do that for about another billion years or so. But that's all the fusion the sun can muster. Its mass isn't sufficient to force carbon to fuse any further. And so, after throwing off its outer layers in a beautiful, if short-lived shroud called a planetary nebula, the sun will end its life as a cooling ball of carbon in crystalline form, a diamond in the sky. But stars that are more massive than the sun have a very different fate. Consider Betelgeuse, the bright red star on Orion's shoulder. This star is probably 10 or 20 times the mass of our sun, and although it's only 10 million years old, it's already approaching the end of its life. You see, the more massive a star, the faster it has to burn through its fuel to hold off the collapse and maintain its size. So although Betelgeuse is only 10 or 20 times the mass of our sun, it has to burn through its fuel 10 or 20,000 times faster. Betelgeuse is a red supergiant star. Notice that it's 1,000 times bigger than our sun. And that means that it's already finished burning all the hydrogen in its core into helium and has begun to fuse the helium into carbon. How much helium does Betelgeuse have left? We don't know. The helium burning phase for a star like Betelgeuse would last about 1 million years, but we don't know when it started. So there might not be a lot of helium left. In fact, it's possible that all the helium could already be gone. When Betelgeuse runs out of helium, the core will of course collapse, putting pressure on the resulting carbon. And Betelgeuse has enough mass to force that carbon to fuse further into magnesium, aluminum, neon, and sodium. Now those reactions emit energy too, but not very much. The energy produced might hold off the collapse for another 1,000 years. Then the core collapses again until it attains a temperature and pressure sufficient to fuse the neon from the previous phase, to fuse into oxygen. But that only produces enough energy to last for about 3 years. And so the star begins its collapse again until it's halted by the fusion of oxygen into calcium, argon, sulfur, and most importantly, silicon. This fusion will last just 100 days, and then the collapse will resume. Now the star has only a week left to live. The temperatures and pressures in its core mount until it reaches a density of over 100 million grams per cubic centimeter. At that density, silicon can fuse into iron. That's the last gasp for the star. One final spate of fusion, one last respite from the inevitable and inexorable collapse which must ultimately destroy it. For 5 days it will furiously burn a full solar mass of silicon into iron. One last chance before the end. But when the silicon is exhausted, the collapse will resume one last time. You see, to fuse iron, uses energy, it doesn't produce any energy. So the iron's not going to fuse, and there's no fuel left that can stave off the inevitable collapse of the star. During the last few moments of Betelgeuse's life, its internal structure will resemble an onion. It will have an outer layer of hydrogen that's not fusing. Within that, there will be a shell of hydrogen fusing into helium, and below that, another shell of helium fusing into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. And at the very center, there will be a nugget of iron growing rapidly. The iron will be held up against collapse by the degeneracy pressure of its electrons. But as we found out in a previous episode, that pressure has a limit, the Chandrasekhar limit. And when the Chandrasekhar limit is passed, the iron core will collapse. Its outer edge will be moving inwards at perhaps 20% the speed of light. Its internal temperatures will skyrocket until inverse beta decay is possible. The electrons and protons within its body will fuse into neutrons, and the degeneracy pressure of those neutrons will be sufficient to call an abrupt halt to the collapse. The inrushing material moving at 20% the speed of light will bounce off that hard core of neutrons and begin to move back outwards at 20% the speed of light, but then it gets fueled by a barrage of neutrinos pouring off that neutron core because of the inverse beta decay. The resulting shock wave tears through the star. The overpressures are such that any element will fuse into any other. Gold, uranium, mercury, platinum, all of the elements we know of are made in this process, and then the star blows its guts up all over the sky, scattering those elements far and wide, making it possible for creatures made of those elements, like you and me, to exist. You don't want to be too close to one of these events, and 50 light years is probably too close. At that range, the incident gamma radiation would probably deplete the ozone layer and expose us to the ravages of the sun's ultraviolet radiation. It wouldn't be good. But don't worry, Betelgeuse is 700 light years away. Not close enough to hurt us, but close enough to put on one heck of a really good show. What kind of show? Well, for several months, you'd be able to see it during the daytime, and it would be bright enough to maybe read by during the night, much brighter than the normal full moon. We'd have a year where the sky would never be darker than dusk. But then it would fade, and we'd look at Orion and see that it was missing its shoulder. The gold in my wedding ring, the iron in your blood, the carbon in our wires, the silicon in our chips, the uranium in our power plants, the carbon in our proteins. All of these elements were made when a giant star blew itself to smithereens and scattered its guts all over the sky. Nothing else that we know of can cram this many protons together into a nucleus. We are all made out of the ashes of dead stars. When is Betelgeuse gonna blow? Well, sometime in the next million years. Anytime in the next million years. Could be today.